All right, back to our cone. Where the circle was sliced through directly with no wibble wobble going on, the ellipse would be if we slice through at a slight angle, but we still are going to cut all the way through our cone. So by doing that, what we create is no longer a circle, but something that's got a bit of an oval quality to it. Oval, sure, but officially speaking, we refer to that shape as the ellipse. As far as the geometric definition, the set of points where the sum of the distances to two fixed points is constant. These two fixed points, again, like the fixed point we saw with parabola, was called a focus. There are two of them this time, so the plural of focus, foci. This is something that you can actually do. So, draw yourself a little line here. Tape a piece of string, not anything with stretch to it, piece of string. Tape a piece of string down at 2 points on that particular line. Pull your pen or your pencil so that the string is now taut. And then start slowly tracing your pen or pencil, keeping that string taut, and you will slowly trace out this ellipse shape. Whatever you're talking about there with the length of your string, the length of your string is fixed. The sum of the distances, right? So from here to here, that's part of my string. From here to here, and from here all the way over, that's still the same length of string that I've got. So the sum of distances, that's fixed. That's constant. The 2 points where I've taped my string down, those are fixed as well. And so if I change the location of where I've taped my string, if I change the length of string that I use, I can get a different looking ellipse. I can get a different looking oval shape. And then, of course, if I, instead of taping it down along a horizontal line, taped it down along a vertical line, I could change the shape of that particular ellipse by having different orientation to it. So, how can we talk about things? Well, smack in the center is the center. The foci, and you look at this picture and say to yourself, okay, well, it certainly looks as though they are the same distance away from the center as one another, and they are, so that's a nice little relationship. We've got the far left and right, because what we can see here from this drawing is that from left to right we have a longer distance than we do from top to bottom. So from left to right, those particular points may be a little bit more noteworthy to us. Well, it turns out we actually have a name for those. We call those vertices. But we do also want to represent that while this is longer from left to right in this particular drawing, from top to bottom, this might be something worth noting as well. So the longer would be the major axis, and the shorter would be the minor axis. And so those would be worth noting. There is a relationship between the letters that we use. You see when you start looking at this list, and let's pull up that full list here from start to finish. Try to keep that drawing in there while still having this complete list here. When you look at each of these lists, you see these letters A, B, and C that appear. The A shows up with our vertices, the C shows up with our foci, the A shows up with the length of our major axis, the B shows up with the length of the minor axis, and then both C and A show up with this thing that we're referring to as the eccentricity. So there should be some sort of relationship here that we can establish, and there is. The B squared is equal to A squared minus C squared. Now what that would mean for us here, A squared The a squared is underneath the x stuff, the a squared is underneath the y stuff. How am I going to be able to tell the difference? Well, if I do a little rearranging here, the a squared would end up being formed from the b squared plus the c squared. These are positive numbers that we've got showing up. B squared plus c squared would give me a number that's, well, bigger than the b squared by itself. So when I look at these equations and I have the a squared and the b squared that show up, the a squared is the bigger number down here in the denominator. If that bigger number is underneath the x, then our ellipse is oriented horizontally. If that bigger number is underneath the y, then our ellipse would be oriented vertically. That observation, as well as the same xy switcheroo that we had mentioned before, allow us to work through each of these situations while only having to remember one. So you can pick whichever one you like. I lean towards when the ellipse has a major axis that's horizontal. The bigger number is underneath the x squared. The center has not been shifted, so the center is the origin. The vertices come from the A, and so those vertices, because this is oriented horizontally, the vertices A comma 0, negative A comma 0. The foci coming from that C number that I would have to calculate. So I would calculate the C. Foci, foci is the cute little thing that I like to tell folks, foci, foci, to remember that it's the C number that I would need, foci, foci. C number showing up there. C comma 0, negative C comma 0. Length of the major axis going to be, again, from the A that was underneath the x squared. The A that's showing up there, horizontally oriented, the major axis horizontal to A. And then finally the B showing up, the only time that the B shows up there in terms of that minor axis, the length of the minor axis would be 2 times B. The eccentricity is going to be based on a little calculation here, C over A, and what that is kind of a measurement of how much or how little of an oval shape we have for our ellipse. Or you could say how close or how far away from a circle our eccentricity ends up being. So we can maybe take a look at a couple of situations and get a bit of an idea of how that eccentricity comes into play. But most importantly, the basic characteristics that we want to list, and this is a longer list, but the basic characteristics that we would want to list out and be aware of: center, vertices, foci, length of the major axis, length of the minor axis, and much more rarely, but still occasionally, the eccentricity. Looking at that right-hand column of information, when the ellipse has a major axis that's vertical, notice that all of those characteristics have had a switcheroo when appropriate. So the center, though it's hard to tell, has had a switcheroo. The vertices and the foci have had switcheroos. The length of the major and the length of the minor axis did not need to be switcherooed. Those are lengths. So no real huge issue there. So if we're given the basic equation x squared over 25 plus y squared over 9 is equal to 1. The first thing that we want to recognize here is what sort of orientation do we have, and that's based on the bigger denominator that shows up. So the bigger denominator that we have showing up is underneath the x. That means that our orientation is that our major axis is horizontal. If our a squared is the 25, that means a is 5. That means that the other denominator is my b squared number. If b squared is 9, that means b is 3. The standard relationship between the a's and the b's and the c's is that b squared is equal to a squared minus c squared. So that would allow us to calculate c. In this particular case, c is 4. So we would have our center. We would have our vertices based on the a value, a comma 0, negative a comma 0. Foci, foci, c would be related to the foci. So foci, foci, 4 comma 0, negative 4 comma 0. The length of our major axis, 2 times a, would be 10. The length of our minor axis, 2 times b, is equal to 6. And again, though it's much more rare, if we needed to, the eccentricity would be calculated using c over a, which in this case would be 4 over 5. Now, if we took the time to actually kind of sketch this out, how far away are our vertices, if our minor axis has a length of 6 and our major axis has a length of 10, how close or how far away does this seem from a circle? The eccentricity is 4/5, so maybe we can get a bit of a judgment here about how much or how little that eccentricity is telling us in terms of being close or far away from a circular shape. So again, that's something that we would have to take a little bit of extra time to examine to try to come up with some useful comments about the eccentricity. But first of all, we do want to focus on the information that we have to provide. And so in this next example, notice that we do not have the normal sort of formatting here in this particular equation. We do not have x squared over a number plus y squared over a number equals 1. The issue here is that we don't have the equals 1. Therefore, let us first try to get the equals 1 and see how things play out from there. In order to start getting the equals 1, we would need to take everything in our equation, oops, that's a 3y squared. We would need to take everything in our equation and divide by 12. So the 3y squared would get divided by 12. The 4x squared would get divided by 12. The 12 would get divided by 12 and give us the 1. Well, now we're liking the 1, but what we would really want to see other than that is the y squared over a single number and the x squared over a single number. And fortunately, in this particular case, the reducing that takes place would give us some nice numbers to use. Y squared would be over 4, and x squared would be over 3. And we have our equals 1. So this means that we are now looking at that more standardized version of our formula, of our equation, and that we can pluck out the a squared and the b squared, and we can lock in the orientation for our ellipse. The bigger number in the denominator is going to tell us which major axis we have. The bigger number in this particular equation is underneath the y, which means that our major axis, like the y-axis, is going to be running up and down, or is vertical. That bigger number being a 4 means that a squared equals 4, so a is equal to 2. The other denominator is my b squared, so that means that b squared is equal to 3, so b is the square root of 3. And again, our relationship here, b squared is equal to a squared minus c squared. So b squared is 3, a squared is 4, and that would mean that c squared would be equal to 1. So c is equal to 1. One of the things that we can make sure that we keep in mind here, the c is going to have to be a smaller number than the a. The foci have to be inside of the vertices. The vertices are the furthest out that we've got with this particular shape. So vertices coming from the a value, foci coming from the c value. So the vertices are going to have to be farther away than the foci. The a value is going to have to be bigger than the c value. So that's a little something that we can utilize now that we've seen a few of these examples. And again, we're talking about the center not being shifted at all at the moment. The vertices come from the a value, and that means because these have to be aligned vertically, they're going to be 0, a and 0, negative a. The foci, those are also going to be aligned vertically, 0, 1 and 0, negative 1. The length of our major axis, 2 times a, which is 2, gives us the length of our major axis, 4. The length of our minor axis, 2 times b, would give us 2 square root of 3. And in this particular case, for the eccentricity, we would use the C divided by A, C over A, and the C over A in this particular case would be 1 over 2. So if we've got an eccentricity now of 1 over 2, again, we can try to start taking a look at what we would have going on here. Are we closer to being a circle shape? Are we farther away from being a circle shape in contrast to our last example? And so our eccentricity in comparison to the last example is that we're looking at a smaller eccentricity. So does the smaller eccentricity end up linking us to something closer to a circle or farther away from a circle? So again, I would encourage you to take a look at that sort of thing, see if you can come up with some sort of connection there that is more specific than what we have said so far. So before we go hog wild here with this last example, shifted forms. Like we've seen already with circles and parabolas, we can shift things around. When we shift things around, the replacements that we're making, instead of x, we have a parentheses x minus h. Instead of y, we have a parentheses y minus k. And in this particular case, I'm directly giving you an equation that already has those. Trying to make things a little bit more streamlined and seeing how everything can fit together with the shifting. So again, the first thing that we're talking about here before we even worry about the shifting is what kind of orientation we have. So we're looking at those denominators. Again, we got the equals 1. Yay. We're looking at those denominators and we're saying which denominator is bigger? 9. 9 is underneath what variable? The y. Y is vertical. So in this particular case, our ellipse is also going to be oriented so that the major axis is vertical. That means that our a squared is 9, so a is equal to 3. B squared is our other denominator, so b is equal to 2. And using our relationship b squared equals a squared minus c squared, we're going to get c squared equals 5, so c is equal to the square root of 5. And that allows us to list out our unshifted information, where we've got our center, our vertices, our foci, our length of the major axis, and our length of the minor axis. Now we would need to shift things. Now based on the parentheses x minus 3, that means that we're shifting right 3. Based on our parentheses y plus 4, we are going to be shifting down 4. So we want to take our list of information and we're going to want to use those shifting directions to alter things. If we take the center and we shift it, now again, we can think of things in terms of adding and subtracting. We can think of things more visually in terms of right, left, up, down. But our center, by shifting it to the right, switch back to the black ink. By shifting it to the right, 3, our center will now start with 3, comma. By shifting down 4, our center will have a y value of -4. In fact, I could say, now that that center has been correctly identified, if I take the center and add it to any of the other points that show up, I can come up with the shifted version of my vertices and my foci. So the center plus this particular point would end up giving me a new vertex 3, -1. And if I take my center and add it to this other vertex, that would give me a new shifted vertex 3, -7. Likewise with foci, adding that center would give us 3, and we could say -4 plus √5. And for the other focus, 3, -4 minus √5. Not super friendly, but nonetheless, that is what it is. Because the length of the major axis and the length of the minor axis are not tied to shifting. Those are lengths. Those lengths are going to be fixed when I pluck the unshifted ellipse off the page and then shift it over, right 3 and down 4. Those lengths are going to remain the same, so that's just a matter of carrying over those values length of the major axis is still 6, the length of the minor axis is still 4, and officially speaking, throwing in that eccentricity, the eccentricity would be the square root of 5/3. Worst case scenario, though we're not doing an example of it here, worst case scenario would be if we needed to go through and do the completing the square steps for the x stuff, for the y stuff. That would be the worst case scenario, and you can see that I did not plan to have that sort of thing in this particular set of notes, but what I am going to do is, because this is going to have a similar feel to what we see in the next video. In the next video, I believe I have an example where we do the completing the square on something that is a little bit more similar to the ellipse type of situation. And so you'll see an example at least of that kind of more worst case scenario of how things work with completing the square, having this more, well, more aggravating circumstance to deal with. But again, notice that largely speaking, what we're talking about here, the same kinds of basic tools all the way through with the parabolas and our vertex focus directrix, our orientation, having the XY switcheroo, with our ellipse, having the XY switcheroo as well showing up here, having the shifting, having the center of the vertices, the foci, the length of the major axis, length of the minor axis. A lot of these things, we're trying to make the same sort of comments to allow us to streamline the information that we would need to remember to the bare bones. What exactly do we have to remember so that we can get through things? I've got to remember my unshifted list of characteristics and how to work them out. If I can remember that and I can correctly figure out the shifting, then I can find the shifted version of those basic characteristics. If I had a different orientation where, well, and we do in this last example, where we're saying our major axis, we remember the version where our major axis is horizontal, and this stuff is all the switcherooed version of that. Everything's getting flip-flopped. That gives us, again, a streamlined way of trying to put things together in our minds to keep it at a minimum.